Okay, chapter 3, day 4, concavity of functions. So we've looked at increasing intervals of increasing and decreasing. We've looked at absolute extrema. And then day 3, we determined relative extrema. Okay, so increasing and decreasing is easy. Pencil up, pencil down, pencil up, pencil down. Now, concavity deals with this shape of the graph. So if you think of a portion of the graph would be like, I don't know, a downward facing cup, then this portion would be concave down. And then from about here to, we'll say this point, my function would be concave up. So maybe for concavity, if we think shape of parabolas, all right, so let f be a twice differentiable function. Now if the second derivative is positive, then the function is concave up. So concave up, think upward facing parabola. If the second derivative of a function is negative, then the function is concave down. So we'll think downward facing parabola. So again, if you've printed the notes, you're good. If you need to copy the notes, please pause the screen. So to determine the open intervals for which a function is concave up or concave down, concavity deals with the second derivative. So we find the critical values now of the second derivative. And what are critical values? Set the second derivative equal to 0 or determine where it doesn't exist. We put those critical values on a labeled number line, but now we'll label the number line as f double prime. Same deal, choose a test number in each interval to determine the sign of the second derivative, and then we make our conclusion. Okay, so determine the open intervals of concavity. So we can't have a second derivative without the first, just simple power rule, 3x squared minus 6x. We don't care for the first derivative right now, so we'll go right to the second. More power rule, 6x minus 6. Second derivative equal to 0, that occurs at x is equal to 1. Second derivative always exists. It's a polynomial, we know the domain is all real numbers. So on our number line, one critical value of 1. If I plug 0 into my second derivative, I'd get a negative value. If I plug in 2 into my second derivative, I get a positive value. So the function is concave up on the open interval from 1 to infinity because the second derivative is positive there, and the function is concave down from negative infinity to 1 because the second derivative is negative. The first derivative told us the intervals where the function was increasing and decreasing. The second derivative tells us about the intervals of concavity, again, on the function. Alright, so another polynomial. First derivative, 2x minus 4. Second derivative is just 2. Okay, no critical values. So if I look at a number line, I have no critical values to put on there. What do we know about the second derivative? The second derivative is strictly positive. So my function will be concave up for all real numbers. And if we go back to what this function looks like, it's the graph would be a parabola. Lead coefficient is positive, so it's a parabola that would open up. So it makes sense that the function is concave up on the entire interval. Now look here. It decreases and then increases, but it only has one type of concavity. So you guys will begin to see these behaviors of the function are very, very different from each other. So a function can decrease and increase, change in direction, and never change concavity. So take a minute, pause the slide if you need to. A point of inflection is the point where the function changes concavity. We use a lot of the same, what would look like the first derivative test to determine relative extrema. So if we have at a critical value the second derivative changing sign, any sign change of the second derivative could be a point of inflection. on the graph of the function. To determine the point of inflection, substitute the critical value back into the original. Now I say it could be because even though there's a sign change on the second derivative, it might not be a point on the function. That's why we always plug back into the original. If there's no sign change, then no point of inflection could ever exist. So we wouldn't even have to test that critical number. Okay, so now let's put it all together. Determine intervals of concavity and the points of inflection. So I'm going to rewrite this as x to the negative first power, so I don't have to use my quotient rule. First derivative, bring the exponent down, subtract 1 from the original. Don't worry about writing that properly. Derivative of 4 is 0, 2x to the negative 3. Now when I write it with a positive exponent, my second derivative will never equal 0. My second derivative doesn't exist at 0. Okay, if I plug a negative value into the second derivative, I get a negative answer. If I plug a positive value into the second derivative, I get a positive value. So my function is concave up from 0 to infinity because the second derivative is positive. My function is concave down from negative infinity to 0 because the second derivative is negative. So a possible point of inflection would occur at 0. So when x is equal to 0, I plug 0 back into the original function and I get 0 plus 1 over 0. Okay, well, 0 is a domain restriction from the original, and we know what number over 0 would look like. It would be a vertical tangent line, or excuse me, a vertical asymptote, so there's no point of inflection. A change in concavity occurs, but it doesn't occur at a point. Instead, on this graph, it occurs at a vertical asymptote. Okay, so let's rewrite this as x plus 2 to the 1/3 power. The domain of this function is all real numbers. Okay, an odd root you can take of a positive and a negative. So first derivative 1/3 x plus 2 to the negative 2/3 power. Second derivative negative 2/9 x plus 2 to the negative 5/3. So now if we were to write this with a positive exponent, second derivative never equals 0. The numerator would never be 0. My second derivative doesn't exist, where the denominator would equal 0, so that would occur at negative 2. Other than that, power over root, you're taking the cube root of a number, so this value can be negative if it needs to. It wouldn't be a domain restriction. Alright, if we plug a negative value, let's say negative 3, that's an easy one for you guys to see. Negative 3 plus 1 is negative 1, so that would give me a negative over a negative, which would be positive. If I were to plug in 0, I would get a negative over a positive, which would give me a negative value. So my function, the answer to A, concave up, negative infinity to negative 2, because the second derivative is positive. Concave down from negative 2 to infinity, because the second derivative is negative. And then possible point of inflection, when we plug negative 2 back into the original function, you get 0. So the point of inflection would be at negative 2, 0. And again, it's a point of inflection on the function. If you plug negative 2 back into the second derivative, you're getting does not exist. That's where the critical number came from. Okay, tan of x, think of where negative pi over 2 to pi over 2. So we're just looking on this domain. First derivative is secant squared of x. So let's write that so you can see the power rule, or power and chain. So your second derivative, 2 secant x to the first. Derivative of secant is secant x tangent x. Alright, we talked about this briefly. Let's rewrite this as a fraction. Secant is a reciprocal of cosine. Tan is sine over cosine. So this would be 2 sine x over cosine cubed of x. Second derivative is 0, where the sine function equals 0 on this interval. So that occurs at 0. Second derivative does not exist, where the denominator would be 0. But between negative pi over 2 to pi over 2 on the open interval, that never occurs. So if we put 0 on the number line, the second derivative, alright, when I look in the first quadrant, sine and cosine are both positive. So I should close this off because there is a domain restriction. So from 0 to pi over 2, second derivative would be positive. Oops, sorry. From negative pi over 2 to 0, in this quadrant, sine is negative, cosine is positive. So I would have negative divided by a positive. So negative interval there. Alright, so our function is concave up on the open interval from 0 to pi over 2 because the second derivative is positive. Function is concave down from negative pi over 2 to 0 because the second derivative is negative. And then the point of inflection, if it occurs, it would occur at 0. So when we plug 0 back into the original function, tangent of 0 is 0. So the point of inflection occurs at the origin. Alright, let's see if we can do one more. So you do need quotient rule here. First derivative, bottom times the derivative of the top, minus top times the derivative of the bottom, all over, bottom squared. So this becomes x squared plus 2 minus 2x squared. So negative x squared plus 2. Alright, so now the second derivative, bottom function times the derivative of the top, minus top function. Now the derivative of the bottom uses the chain rule. So bring down the exponent of 2, subtract 1, and then multiply by the derivative of the inside, all over the bottom squared. Alright, so now let's get some things to cancel. I have x squared plus 2 to the first, x squared plus 2 squared, x squared plus 2 to the fourth. So these can all reduce by 1. Alright, so again, if I have, only when I have the exact same thing common in all the terms. So now we have negative 2x times x squared plus 2 minus 4x times negative x squared plus 2 all over x squared plus 2 cubed. Okay, so in the interest of time, your homework, answer the question. Answer the question. Alright, concavity and points of inflection. See you in class.